Using the table, estimate the total distance traveled from time t equals 0 to time t equals 6 using left, right, and trapezoid. Actually, we're also going to do midpoint, so we're going to add one to it. We're going to do one better. All right, so we'll start off with the right and the left. Before we do that, though, let's take a look at what this table is telling us. All right, so another way that we could write this as the definite integral from 0 to 6, v of t dt. So we have v of t is the function, d of t is the variable of integration, and we'll spend a lot more time talking about that in upcoming lesson. So right now I'm just giving you some giving you some notation and explaining what it means without necessarily breaking down every part. In later lessons I'll break down each part. So that is approximately the distance traveled from 0, actually is equal to the distance traveled from 0 to 6 seconds. We're going to approximate the distance traveled from 0 to 6 seconds using a left Riemann sum, a right Riemann sum, a midpoint Riemann sum, and then a trapezoid, the trapezoid rule. The definite integral itself gives the exact value. All right, so here we have, it doesn't really tell us how many subdivisions to use, subintervals to use, right? But if you look at the data, right, there are 7 pieces of data there. Right? So that means if you have 7 pieces of data, you can make 6 rectangles. You can make 6 bars. Right? Bar 1, lovely bar there. 2, 3, 4, 5, 6. I can make 6 bars. Right? We would want to use as much of the data as we could. Right? So we're going to use 6 will be our number of values. For the left Riemann sum, we're going to use the values on the left-hand side. Right? And so the values on the left-hand side would be, for this bar, the first bar, it would be 3. And then for the second bar, it would be 4. And for the third bar, it would be 5, and so forth. So I'm going to actually just underline, make it a little bit easier. For the left Riemann sum, we're going to use these 6 values, right? The left-hand side for each bar. Now, before we can do anything, though, we do need the change in x. So the change in x is 6 minus 0, and we're doing 6 intervals, so that's just 1. Right? And we would have 3 plus 4 plus 5 plus 4 plus 7 plus 8. Right? So the left Riemann sum, you got 15, 20, 28, 31. Let's find the right Riemann sum. Right? So the change in x is going to be exactly the same, right? Oops, I wanted that to be purple. It didn't come out purple. How about now? Yes. Right, so it'd still be 1. And now we would use the right-hand values for the right Riemann sum. So that would be 4 plus 5 plus 4 plus 7 plus 8 plus 11. All right, so that's going to be 15, 26, 39. All right, so we have the left-hand Riemann sum, the right-hand Riemann sum. If we look at the velocity, notice that it's not everywhere increasing. Right? The values aren't necessarily getting larger and larger. They do dip down a little bit, although the overall trend is that they're getting larger. Right? We're not going to look at really overestimating and underestimating in this lesson. We're just going to review how to find all of our different Riemann sums. So now let's do a midpoint Riemann sum. Now for a midpoint Riemann sum, we need to have middle values. Right? So our bars are going to be like this. Right? They're going to be, there's 1 bar, so that we could have this in the middle. And then here's our next bar, so that this is in the middle, and then our last bar, so this is the middle. You can't be a midpoint if you're not in the middle, right? So our change at x this time, we still have 6 minus 0, but now we only have 3 subintervals, so that's going to be 2. So for the midpoint Riemann sum, we have 2 times 4 plus 4 plus 8. So that's going to be 16 times 2 is going to be 32. So notice it's not an average of those values, right? It's we take the value in between. We're taking the midpoint. Not the left hand. So if we had 3 bars, not the left hand side, not the right hand side of the bar, but the middle of the bar. Now let's do the last one, and now let's do trapezoid rule. So the trapezoid rule is the only one that's going to use all of the values. Right? We're going to use the first value one time, right? And then we use all the values in the middle twice, and the last value once. Right? So it's like those end values are going to be just used once. So it's like we have the left Riemann sum and the right Riemann sum, like we have those rectangles, and we're averaging every one. Right? So if we're figuring out a trapezoid, right, we would use this side and this side, we'd add them together, divide by 2. And then we'd go to the next one, right? And we would use this side and this side, add them up, divide by 2. Well, you see we used that second value twice. And the same thing is going to happen for every value except for the middle value. Right? So for the trapezoid rule, we have change in x will be 6 minus 0 divided by, so we have 6 subintervals, but then we're averaging because we're using the values more than once. So we have 2 times 6 in the denominator. So that's going to be 1/2. Which makes perfectly sense because if we were figuring out the area of a trapezoid, right, we take 1/2, the sum of the bases, times the height. Right? So this is like a trapezoid flipped on its side there. The height, is the distance between the bases, is going to be the change in x, and the bases are the values of the function. So trapezoid would be 1/2 times, actually I need to move that over a little bit, make sure I've got space for all these values, right? So we have the first value gets used once, and then every other value except for the last gets used twice. So 2 times 4 plus 2 times 5 plus 2 times 4 plus 2 times 7. I knew I didn't have enough space. Plus 2 times 8 plus 11. Let's see if I can squeeze a parentheses in there. So that's going to be 1/2 times 3 plus 8 plus 10 plus 8 plus 14 plus 16 plus 11. All right, so that would be, so you got 30, 40, 56, 59, 70. And then half of 70 is going to be 35. Interestingly, halfway in between the left and the right. So here we have all the different ways and what we've calculated here. So let's put some units on all of those now that we've calculated them. This one is, so all of these are, this is in, does it say, let's just call it miles per minute. Miles per hour, I don't know. Miles per hour. So this would be 31 miles in 6 hours. And this would be 39 miles in 6 hours. And this would be the total distance. So 31 miles, that would be total distance, right? So 31 total miles in total. Took 6 hours to go 31 miles. 6 hours to go 39 miles. 6 hours to go 32 miles. And then 6 hours to go 35 miles. Now all of these are approximations. Maybe one's exact, but chances are they're all approximations, right? And in a later lesson, we're going to learn how to, now we've learned how to approximate, we'll also learn how to find exact values. Now, in a problem like this with a table, we would only have approximations, right? This is all we could do, right? With a function, we'll learn ways that we can actually find exact values as well for area under a curve, right? So some concluding notes before I end this video. The first is looking at overestimating and underestimating for midpoint and trapezoid. So if the graph is concave down, then the trapezoid rule is an underestimate. The midpoint is an overestimate. Right? So probably have that in your notes if you don't have it in your notes. This is the basically saying the trapezoid rule underestimates and the midpoint rule overestimates, and that's if it's concave down. And here the reverse is true. If it's concave up, then the midpoint rule underestimates and trapezoid rule overestimates. All right, so I'm going to end this tape for now, and then let's do a few practices with figuring out whether the approximation is an underestimate or overestimate, and then I have some concluding remarks.